your Group 2, and we're here to present our Capstone project, IoT-based air purifier with air quality monitoring system. According to Rodman 2021, air purifiers primarily consist of filters and a fan that sucks in and circulates air to trap pollutants and particles before pushing the clean air out into the area. Our own air purifier not only focuses on filtering the air, but also on monitoring the air quality of the surroundings using sensors and other platforms.
Our project is also based on IoT, or the Internet of Things, which is defined by Oracle Philippines 2020 as a network of physical objects embedded with sensors, software, and other technologies to communicate and exchange data with other devices and systems via the Internet.
Our air purifier is comprised of sensors that detects harmful gases, filters that traps particles, an exhaust fan that suctions air from a room, and other components and boards that work together to keep the air purifier working.
The air purifier aims are as follows. First is to cleanse the air and improve the air quality by removing pollutants so we can breathe in a healthy environment. Second is to monitor the air quality in the room using IoT analytic platform service. And finally is to reduce the likeness of health problems caused by gas particles in the air.
Our purifier uses an IoT analytics platform called Capstone to give real-time representation of data from sensors that use ESP8266 Wi-Fi module. According to the Crocus 2021, an ESP8266 is a SoC microchip that is primarily used to construct endpoint IoT or Internet of Things applications.
Since ThinkSpeak represents raw data, it displays the following. First, the graph and condition of the exhaust fan. Second, the carbon monoxide readings in ppm. Third, the dust density or concentration readings in micrograms per cubic meter. And finally, fourth, the carbon dioxide readings in ppm.
This also uses an online platform for developing applications for Android phones called MIT App Inventor, which is simple to use as long as the phone is linked to a specific Wi-Fi network. Moreover, MIT App Inventor also includes our own customized design for our applications, as well as program that turns the exhaust fan on and off.
This air purifier is programmed using an open-source electronics platform called Arduino. Arduino is a lot more efficient means of programming a robot because it has a commands that students like us can understand. Moreover, this air purifier made some integration with Arduino Mega 2560 board and ESP8266 Wi-Fi module. In short, the Arduino Mega 2560 board has its own program, and so does the ESP8266 Wi-Fi module. Moving on, this air purifier also has 3 sensors: MQ135, MQ7, and Optical dust sensor.
Let's talk about the MQ135 sensor. The MQ135 has a wide range sensitivity to harmful gases, as well as benefits such as a long lifespan, low cost, simple drive circuit, and so on. This sensor detects the following gases:
Following that is the MQ7 sensor. In terms of sensitivity over a wide range, the MQ7 sensor is comparable to MQ135 sensor. The only difference is this sensor exclusively measures carbon monoxide levels.
And finally, the optical dust sensor. It is a dust sensor with an optical sensing system. This indicates that this device contains a infrared emitting diode or IRED and a phototransistors that are diagonally placed. And it detects the reflected light of dusts in the air.
The IoT-based air purifier with air quality monitoring system employs three sensors: MQ135, MQ7, and an optical dust sensor to identify certain gases and particles. Heating the sensors takes 30 to 45 minutes to achieve at least accurate readings.
This system employs an exhaust fan and two filters, a high-efficiency particulate air filter and a carbon filter. The exhaust fan draws in air filtered by the two filters.
There is also a stage of preheating the sensors based on datasheet's information. Preheating is critically, particularly for MQ7 sensor. This will entail heating the sensors at 5 volts for 60 seconds, followed by heating at 1.5 volts for 90 seconds. Preheating is also the stage at which sensor sensing process begins.
When the three sensors detect something, the results will be presented on the LCD screen, indicating whether it is normal or whether high gas levels have been detected. The buzzer will sound when gas levels rise to harmful levels when exposed to human body for an extended period.
We base the harmful levels on web pages we obtain. The alarm level for MQ135 sensor is set to 1000 parts per million, the MQ7 sensor to 9 parts per million, and optical dust sensor to 35 micrograms per cubic meter.
Ratings will also be sent to TeamSpeak, where our data from one air purifier will be shown. Each air purifier will have one TeamSpeak channel and one MIT app inventor application. This app will have two buttons for turning on and off the exhaust fan. The TeamSpeak platform also offers a channel sharing function that gives you different options when you're sharing your channel with others.
Moreover, these air purifiers will be placed in different rooms to gather room readings and data to determine the air quality.
The state of the exhaust fan is shown, with number 1 indicating that the air purifier's fan is turned on. This also demonstrates that the exhaust fans of the air purifiers in the library, computer room, and stock room remain turned on.
In terms of other data, carbon monoxide levels in parts per million range from 0.01 to 0.05 in the library air purifier from May 24 to 26, 2022, which is acceptable and safe given that normal levels in houses without gas stoves range from 0.5 to 5 parts per million according to EPA 2021. Moreover, the carbon monoxide level in the computer room air purifier ranges from 0.01 to 0.04 parts per million. Carbon monoxide levels in the stock room range from 0.01 to 0.08 parts per million. Even though the readings in each room vary, the levels of carbon monoxide in such rooms are likewise safe and healthy.
The library values for dust density or dust concentration varied from 0.00 to 0.1 micrograms per cubic meter. The computer room's reading range from 0.00 to 0.2 micrograms per cubic meter. Because the readings for the two rooms contain 0.00 micrograms per cubic meter of dust particles and the type of graph is in the column in ThinkSpeak, the level of 0.00 micrograms per cubic meter is not displayed.
The dust concentration readings in the stock room range from 0.01 to 0.10. According to the Indoor Air Hygiene Institute 2021, dust levels of 12 micrograms per cubic meter or below are considered healthy, with little to no harm from exposure. However, the stock room contains more dust particles than the other rooms, which explain why its values are higher than the other two. However, the dust density or concentrations in the three rooms are likewise at a safe and healthy level.
Moving on, carbon dioxide levels in the library room varied from 426 to 440 parts per million, 431 to 440 parts per million in the computer room, and 417 to 449 parts per million in the stock room. There isn't much of distinction between these levels in each room. Moreover, these carbon dioxide levels are taken at night, when all of the monitored rooms are closed.
Because we all know that humans emit carbon dioxide and scented particles travel through the air through a process known as diffusion, in which they are constantly moving and later spread out through the air around them. The readings may vary depending on the number of people present and the chemicals sprayed into the atmosphere.
But still, those carbon dioxide level in parts per million are considered safe because according to the Wisconsin's Department of Health Service 2021, the usual level of carbon dioxide observed in occupied space with good air exchange is 400 to 1000 parts per million.
In general, the levels of carbon monoxide, dust density or concentration, and carbon dioxide in the library, computer room, and stock room are safe. So there is no need to be concerned about the health of those who stay there.
IoT-based air purifier with air quality monitoring system is hugely vital and far more advantageous because it is based on IoT and employs application and platforms to achieve efficient processes. And that concludes our presentation for our Capstone project. Again, we are Group 2 of Grateful Fate of Tansa Child Development Center. Thank you for listening.